Hello, I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology. In this video, we will try to understand the basics about Thevenin's theorem. And first I will cover the statement of the Thevenin's theorem, then its explanation part, and then we will try to solve the sums based on the Thevenin's theorem. I will begin with the statement of the Thevenin's theorem. The statement is that for a linear bilateral active network, the Thevenin's theorem is applicable to only linear network, bilateral network and active network. Current flowing through the load resistance is given by expression here. This is the expression. IL is equal to VTH divided by RTH plus RL. IL is equal to VTH divided by RTH plus RL, where this VTH is Thevenin's equivalent voltage calculated at the output terminals when the load resistance is removed. Means we have to remove the load resistance and we have to find out the potential between the terminals A and B, and that is nothing but the VTH. I will explain later on in detail. Then RTH is the Thevenin's equivalent resistance calculated at the output terminals when load resistance is removed and all sources are replaced by the respective internal resistances. Internal resistance of the voltage source is 0, internal resistance of the current source is infinite. We have to do all these formalities. This main important thing in this particular theorem is the calculation of the two values, VTH and RTH. And when we know the value of the VTH and RTH, then complicated network is replaced by the Thevenin's equivalent network, which is very same as this, which is same as the simple voltage source having its internal resistance. This will be the RTH and this will be the VTH, and reconnect the load which is removed in the first step. That will be the final circuit. Now I will take one simple example here, and in this particular case we will try to find out, or we will try to understand the Thevenin's theorem explanation. Thevenin's theorem or problems on the Thevenin's theorem can be solved in the 4 steps. Problems on the Thevenin's theorem can be solved in 4 steps. The step number 1 is can be solved in the 4 step. Step number 1 is remove the load resistance and redraw the same circuit. This is the step number 1. I will start with step 1. Step 1. Remove the load resistance and redraw the same circuit. Now here, if we are removing the load resistance and we are redrawing the same circuit, circuit will be something like this. Here, we are removing the load resistance and we are redrawing the same circuit. It will be something like this. Here is A terminal. This will be the B. Here it is R4. This is R5. Here it is R2, this is R1, and it is R3. We are removing only the load resistance, remaining circuit is the same. First simple is as simple as. Now, the step number 2 is, just I will mention the steps for understanding purpose, nothing else. Calculation of VTH. Calculation of VTH. Calculation of VTH. Now here, what is the VTH? I will go to the statement of the VTH and then I will come back to the original figure. Thevenin's equivalent voltage calculated at the output terminals when the load resistance is removed. Means when we will remove the load resistance, the circuit will be something like this, and we will calculate the potential between the terminals A and B. That is the value of the VTH. Now, if we are finding or calculating the potential between the terminals A and B, then here we have to travel from the terminal B towards A, because VTH is VAB, that is B to A. Sometimes we can calculate A to B, but generally we are taking its modulus value to avoid the confusion of the sign. Now here in that case, if we are calculating this potential, how will be its value? This voltage may be plus or minus, this voltage may be plus or minus this particular voltage depending on the polarity of the current. The current in R4 is 0 because it is open circuit. Current in R5 is 0 because it is open circuit. Means here current in R2 is important. That's why we have to calculate current in the figure. Now here in this figure we have the single loop. That's why I will assume it has a current I, maybe clockwise or anti-clockwise, and we will apply the KVL here, that is plus minus. We will mark the terminals depending on the direction of the current, and we will apply the KVL if we are traveling from this point into the loop in the upward direction. How will be the KVL? Now here if we are traveling in the upward direction, negative to positive, which is plus, this is V, then positive to negative, which is minus. The voltage across this resistance R1 will be, it is I into R1. Then positive to negative, which is minus. This resistance is again I into R2. Then we are coming back, positive to negative, which is minus. It is I into R3, which is equal to 0. This is the application of the KVL. And from this equation, we can separate the terms. That is V is equal to I shifting on the next side and taking as a common. Then it will be R1 plus R2 plus it is R3. From this we can calculate its current. I is equal to V divided by it is R1 plus it is R2 plus it is R3. This will be the equation number 1. Now here if we know the current, then we can find out the value of the potential VTH. Generally, I am taking it as modulus value to avoid the confusion. But if we are interested in the polarity of the Thevenin's voltage, then we have to travel from the lower potential towards higher, means B to A. Now VTH, we are traveling in this direction. Potential across this R5 is 0 because current in that branch is 0 because it is open circuit. Then negative to positive, which is plus. The value of the current in R2, which is I into R2, because already we have calculated here I. If the values of V, R1, R2, R3 are known, I will be some finite value. Then again, we are traveling in this direction, which is again plus or minus 0. This is 0. This is the value of the VTH, which is equal to I into R2 is the value of the potential. VTH, that is Thevenin's voltage. Now here, while calculating this value, we can follow any path, maybe this path or maybe this path. Again, potential will be the same, but we will use generally the shortest path. That is the calculation of the VTH. Now here, if we know the value of the VTH, then next is the calculation. Now here, step number 3, third step. Calculation of RTH. Calculation of RTH. That is calculation of the Thevenin's resistance. Now here we will see what is RTH or Thevenin's resistance. Here look at Thevenin's equivalent resistance is calculated at output terminals. Means we are calculating at this output terminals. When the load resistance is removed and all sources are replaced by the respective internal resistances. Means here if I am coming to this figure, in this case, if this load resistance is removed, something like this, and all sources available in this particular figure, which is V only, should be replaced by the respective internal resistances, and we are able to calculate the value of the RTH. Here, the calculation will be something like this. First source is replaced by its internal resistance, means figure will be something like this. Here, it is A terminal, this is B terminal. Here it is R4, this is R5, this is R2, Here it is R1 and this will be the R3. Now we have to look at the series and parallel combination to calculate the resistance between the terminal A and B, which is known as RTH in this direction. We want to calculate the resistance here. The circuit will reduce from opposite direction, from this side. Now here these two resistances are in series. There will be the chance of the confusion for the beginners that maybe the series or parallel. For series, simple circuit is that if we are passing the current from here, if the current for both is the same, then these two resistances are in series combination. This here, its next figure will be something like this. Here, this is the figure. Here is again A, this is B. Here it is R4. This will be R5. And here, this is, I will call it as RS, which is R1 plus R3. Here it is R2. This is RS, that is series combination. Something we have to name it RS. Then again we are able to reduce the circuit further. If these two resistances are parallel, now here its next figure will be something like this. This is the next figure. This is the next figure. Here is A terminal, this will be the B. Here it is R4, this is R5, and this is RP, parallel combination of RS and R2. Then its parallel combination will be RS into R2 divided by it is RS plus R2. Parallel combination will be RS into R2 divided by RS plus R2. Now here, now it is simple series circuit. That's why we can find out its RTH, which is equal to R4 plus RP plus R5. And when we know the value of the VTH and RTH, we have calculated both values. Look at here. We have calculated VTH, we have calculated RTH, and if we know both values, VTH and RTH, there will be the final step. That is step number 4. When we know the VTH and RTH, then complicated network is replaced by the Thevenin's network. Thevenin's network. We will draw the Thevenin's network and reconnect the load resistance which is removed in the first step. It will be something like this. Here, this is RTH which calculated. This is VTH which we have calculated, and here it will be the load resistance RL which is removed in the first step. Now here we can calculate its load current IL. What is the formula for IL? Single loop, total voltage divided by total resistance. Total voltage is VTH divided by total resistance is RTH plus it is RL. And this is very same as the statement of the Thevenin's theorem. What is the statement of the Thevenin's theorem? The current flowing through the load resistance is given by VTH divided by RTH plus RL, which we have from this particular figure itself. Now here, this current flowing through the load or current in this loop is VTH divided by RTH plus RL, that is total voltage divided by total resistance, which is RTH plus RL. This is the stuff for Thevenin's theorem. In the next video, we will try to learn or try to understand how to solve the problems which are based on the calculation of the current in the branches based on the Thevenin's theorem. Thank you. That's all.